on your degrees of freedom. With Z values, the Z value 1.96 is always your two-tailed critical value. That's not true with T. With T, your critical value will change depending on your sample size. And so this accounts for the fact that we talked about different sample sizes make significance easier or harder to find, right? So you can get a really extreme, if you only take 2 people, I can find 2 people that are really tall and get a really high average height. But that's kind of a cheating way to get a sample that looks really significant, right? So the t-test makes it harder. If you have small samples, you get fatter tails. It's what they call a Cauchy tail. Fat tail distributions are called Cauchy. Not couch, it's C-A-U, named after a dude. So these fat tails, so you see when you have 1 degree of freedom, that means you have a smaller sample size, because sample size and degrees of freedom are linked, okay? So if you have a smaller degree of freedom, you have a smaller sample size, okay? So with only 1 degree of freedom, you see that that orange one has the fattest tails. You see that around the bottoms? Which means you have to get further out to become extreme, right? Because the tail doesn't become really small for quite some ways. Does that make sense? Now, here's the thing though. Gauss had started with the normal distribution. When degrees of freedom equal infinity for a t, the t distribution equals the z distribution. So, the black one with infinity degrees of freedom is perfectly normal shaped. And look at how quickly those tails approach the axis. Right? You see how quickly they approach the x-axis compared to when you don't have infinity degrees of freedom? So as a reference, how the t-test is harder to find significance for small samples because they could be wonky a little more easily, right? The tails get fatter as you have smaller samples, right? You see that? They're less peaked, so there are less scores in the middle and more scores in the extreme. And it goes back to the logic that we all intuitively get. 1 person 6'7" could happen. 25 people average height 6'7", that's kind of crazy. If I told you I found 1,000 people average height 6'7", you'd be like, what? You know what I'm saying? Okay, so when you get bigger samples, scores become extreme more quickly, and that's accounted for in the approach of the x-axis here, right? Scores more quickly become unlikely. That's what it means when it converges on the x-axis more quickly, right? You have small samples, scores that seem wonky don't become extreme so quickly, right? We kind of hold, because listen, you have less evidence. You only have a few people. We need to be a little more reserved in deciding that this is meaningful when you just have a little group, right? So that's exactly what the t-distribution does. By adjusting for degrees of freedom, Gauss had solved the problem of having different sized crop yields and plants and different sized fields, and he adjusted for that so that, because listen, it costs a lot of money for an organization like Guinness that's international to change its production techniques, right? So if you're going to change all those techniques, you need to make sure your new one works, right? You don't want to do it on a fluke of a couple small samples, right? And you don't want to, if you have a technique that works right now pretty well, you don't want to give up a bunch of your production space to a new strategy that you don't know will work, right? So you want to be able to test on a small area and make that comparison to this big group you already have, right? This solves all those problems for them. Whereas the Z doesn't handle the issue of sample size, right? Not directly. Does that make sense? So here this math solved the issue, and it solves the issue for us when we do studies, and it's really hard. For example, you know, if you're trying to look, you know, if you're trying to be a nurse and you're looking at health research, getting people with weird chronic illnesses to be willing to come in and go through experimental protocols isn't easy. So when we do true research studies for new drugs, they start small. You know, you don't try a new drug out on 1 million people. You know, you get 15 people and you try it out on them. And you want to be able to adjust for the fact you have a small group of people to appropriately balance that test, right? So it applies to all the ways we use statistics nowadays to solve that issue, okay? So, degrees of freedom again, what are our 2 rules for degrees of freedom? Because we know we have to be able to calculate them for a t-test. What are the 2 rules? We covered them again on Tuesday night as a review.
Start with N.
Start with N, beautiful. Which is why I said degrees of freedom and sample size are always linked. If you have a smaller degree of freedom, you had a smaller starting sample size. Okay? What's rule 2? Every time you make an estimate, you lose a degree of freedom, right? It costs a degree of freedom dollar to buy an estimate. Okay? Because in statistics, we buy the estimates, right? They're not free. Okay? So we spend DF for estimates. However you want to write it. Every time you estimate, you lose a degree of freedom. Okay? Now, remember, so we have in the numerator our estimate, in the denominator our standard error of the estimate. So when you're trying to figure out how many estimates are there in a t-test, all you need to do, look at the numerator, because that's where your estimate is, and see how many estimates are there, right? Now remember, there's a difference between a parameter and an estimate, right? Remember that difference? Yes? Okay, so how many estimates are in the numerator of a one-sample t-test? 1. For a one-sample t-test, degrees of freedom will always equal n minus 1. That's it. That's all there is to it. Okay? And that should seem kind of intuitive because that's the exact same thing that happened for variance. Remember? Why was sample variance n minus 1? Because sample variance is numerator, right? Had one estimate in the numerator, right? And so your degrees of freedom for sample variance were 1. N minus 1, right? You lost 1 degree of freedom for your one estimate. Same thing here. There's one estimate. This is a parameter, not an estimate, right? Okay. One estimate you have to make here. Okay. So you start with n. You take away the one estimate. That's it. This will always work. Okay. It will always work if you can identify what's my estimate, what's my t-test. Okay. You look and say how many estimates am I making. Once you do that, you just take that away from n. Okay. For t-tests, there are only 2 equations. One sample is n minus 1. Related sample is n minus 1. Independent samples is n minus 2, though. Remember how we talked about that on Tuesday? Because then you're comparing 2 groups, so you have 2 estimates to make. Boys versus girls, for example, right? So, I mean, if you want to just memorize n minus 1, n minus 1, n minus 2, you can do that. But like I told you, when we get into our next world, that starts to get more complicated, which is why I try to give you both ways. I give you what this logic works for me. I like to think conceptually about statistics. Some people don't like thinking conceptually about math. They just want to memorize stuff. If you want to memorize stuff, one sample t-test, n minus 1 equals df. There's your equation. Okay? You do what works for you. But just know, if you're going to memorize equations for degrees of freedom, we're going to probably end up with, we have spot 6 equations for degrees of freedom, I think, before this class is over, if I'm counting right now in my head. So they'll be a little different every time. Okay? But it goes always back to this logic.
Real quick, what was like 2.68 for?
An example of how you report a z-test versus how you would have to report a t-test. Noting that on a z-test, there were no degrees of freedom, so it's just an illustration. On a t-test, you have to report your degrees of freedom in parentheses. You can't just write t equals something. You have to write t, degrees of freedom equals. Because I can't know if that value is significant unless I know how many degrees of freedom this t had, because the distribution changes shape.
Okay.
The z never changes shape, so I don't need to know anything except for the z value. So trying to highlight the slight differences between z and t. Okay? So, for example, if we were using the blue line here, you would write t parentheses 5, because that's the degrees of freedom for the blue distribution here, and then you would give the value. Okay? As a note, technically in APA style, there is not a space between t and the parenthetical statement. Okay? The parenthetical statement runs right into t, no space. Okay. So it is a new distribution, only in the sense that it is a modified normal. And normal is modified by degrees of freedom. Does that make sense to everyone? Everyone kind of gets that? Okay. So we start at the normal, but we never have infinity degrees of freedom, right? Like, it just doesn't happen. If you had a question that said, imagine T has infinity degrees of freedom, what's the critical value? Well, listen, you can't go into the calculator and type in infinity, right? So you have to realize, oh, they're trying to trick me. Because if T has infinity, I can just use Z. So then look up your value in Z. Does that make sense? Okay. Cool. Any questions about, and so you should be able to intuit, for example, critical values are going to be similar, right? And the bigger your sample size, the closer your T critical value would be to a Z critical value, right? So if you have a sample size of like 100 people, your critical T is probably going to be like 2.05, right? Whereas the two-tailed critical T, plus or minus 2.05. Whereas if you remember, our two-tailed critical Z is plus or minus 1.96. Those numbers are really close to one another, right? But if you have very few degrees of freedom, your two-tailed critical T might be 2.8, right? A much bigger number, because the tails aren't going to converge on the x-axis as quickly. Does that make sense? But you still have two tails, because it's normally shaped, right? The further you get from 0, the more extreme the score becomes. All that same logic still applies to the T distribution. Okay? Does anyone have questions about that? Okay. So the one sample test is the first one we're going to talk about. Again, you have to remember the logic of this is you have one group of people, one sample, and you have to have an expected value to compare to. Okay? Now, depending on what you're doing, like in the homework we're going to do, you have to read the instructions. Because think about it. I would not use the same population expected value for weight as I would for height, right? People have a different average population height than they would average population weight, right? So you've got to think about, make sure you look at and find the correct expected value, right? If you're dealing in this realm, it's going to be like when you were doing a z-test and they told you, you know, mu equals, or the population value is, or the expected value is, right? They're going to give it to you. Because you are always going to be using what we call an a priori, that means given beforehand, right? A priori, prior, before, just Latin, an a priori value, okay? So it's going to be a value that they had beforehand to give you that you test your data against. Does that make sense? So you're dealing with one group of people as your source of data, comparing it against this expected value. Okay. So what does it look like? It looks like this. Okay. So again, measuring UAs for comparison against an expected value. Remember UA, unit of analysis, just basically a participant, right? Units of analysis are the individual items that make up a sample, right? And samples are a subset of a population. All goes back to the logic we introduced in the beginning of class, or the jargon. And remember, I told you that I was going to give you this is what I call the universal t-test. Every t-test uses this logic. This is what it's doing. And so if you can think about, what's my estimate? What am I comparing to? What's the standard error of the estimate? Every t-test uses that structure. Okay, but again, if you don't like thinking about the math conceptually and logically, if you want to think about the math as memorization, this is the equation. Okay, now I want to make sure we remember, what is this guy in the denominator? If he was standard deviation, would he just be an S?
Is it standard error?
Bam! Yes, because it is the standard deviation of the sample mean. A standard deviation of a statistic is a standard error, right? So you have a statistic here that identifies who this belongs to, right? That's what that subscript means. Remember Y subscript I is, subscripts in statistics are like name badges. They just tell you who this belongs to. Does that make sense? So when we have y sub I, we're just saying a score that belongs to somebody, right? It's just a name badge. Put your name here, okay? Here, we're using the same logic with our subscript. A standard deviation that belongs to somebody. What does it belong to? The sample mean, right? It belongs to a statistic. Again, this is why I tell you both the definition and the math. A standard error is the standard deviation of a sampling distribution. A sampling distribution is the distribution of any statistic for a sample, all samples of size n from one parent population. Blah, blah, blah. You're like, what? Okay. All that says is, anytime you're dealing with statistics and not scores, it's not just a standard deviation. It's got to be a standard error, right? So if you ever see a subscript stat, it means standard error. If it means standard error, this is what it equals, right? This is the mathematical formula for standard error. That's why I write this, I write that. It means the same thing. Can everyone see that they mean the same thing? Okay, so like however you saw that written, you should not get tripped up. If I choose to just write standard error in here and not write out what standard error is for you, you should still know that's standard error. Don't just divide by standard deviation, right? And again, every single, if you just think about back to the conceptual, every single one is estimate minus parameter over standard error of an estimate, not standard deviation, right? So this is always going to be a standard error term, right? For a t-test. So, again, the math works out very similarly. Only slight difference is an estimate. So, we have very, very small differences. We have a more or less normal distribution. It just changes its shape based on sample size, right? Small difference. So, because it changes by sample size, we have to report degrees of freedom for it. Okay, that might be a bigger difference because you're not used to dealing with that very much. Okay, mathematically, calculating it, the math is the same. You just have to get your standard deviation term from your data instead of being given it ahead of time. Does that make sense? So again, small difference. So you have two really small differences. So if you got Z, there are really, really small permutations on that. And one kind of new thing, putting the degrees of freedom in there, which is why when we talked about sample variance, I tried to make sure we started the discussion on degrees of freedom because I told you it would come back and then stick with us. And it will be with us for the rest of class. We will have degrees of freedom for all of our tests moving forward. Okay? Okay. Questions about the math. So we got the distribution, we got degrees of freedom, we got the math. Everyone feel like they understand those ideas? Everyone feel like they understand the concept of the design. We use this when we want to do what? What does the math do for us as a comparison?
Takes a large set of data. Right.
Well, we can use small data. That's the beauty of the T, is it lets us have small data or big data because it adjusts for that, right? We just need a group, right? If I wanted to compare Arizona education performance to New Mexico education performance, could I use this?
Yeah.
Why can't I compare New Mexico to Arizona using this?
Oh, be
Hit it, Delaney.
it's a one sample.
It's a one sample. If I'm comparing New Mexico to Arizona, that's two groups of data that I'm comparing against one another. If I wanted to compare Arizona's education system to the expected performance of education for the United States on average, could I use this test? Yes, because you have an a priori expected value of what they should be doing, right? So if the government says you need to have, an average graduation rate of this, right? That's the expected value, right? Ahead of time, this is where you're supposed to be. And if I want to know, is Arizona achieving that? I could check our graduation rate against the expected and determine if we in fact are meeting it or if we're significantly above or below that expected value. So you got to ask yourself, are you talking about two groups of data and you're analyzing them both, or are you talking about one group of data and one number that you're comparing it against? Okay? A one sample test, it's one number. And they give you that number and you compare your stuff to that number. Okay? If you have more than that, if you have two sets of data, you're into an independent test world. And things change then. Okay? Does that make sense? Okay, so again, we got to keep the design straight now. Because if we don't keep the design straight, things get kind of complicated moving forward. Because design becomes really important now to figuring out which test do we use. Because we're going to start multiplying tests. We're going to have all kinds of tests. And you're going to have to figure out which one to use when you go to take a quiz, right? I'm not going to write for everyone, using this test, do that. I'm going to be like, here's your problem. You have to figure out what test to use based on the design, okay? So we need to start making sure we understand the designs of these things. So, one sample test, one group of data against an expected value, and all t-tests. The other important design factor about all t-tests is they expect you to have an outcome. Remember, input, output? I told you we're going to need to be thinking about that. An outcome, an output, a criterion, a dependent variable, whatever you want to call it, right? The output side of the equation, right? It should be continuous, interval ratio. Like, it shouldn't be categories. You don't use a t-test to predict eye color, okay? You use a t-test for things like weight, things like GPA. You don't use a t-test for predicting ethnicity, okay? Things that exist as categories instead of as scale cannot be predicted by a t-test. We have to do something else. We'll talk about that before class is over, okay? Your outcomes are expected to be scale, interval ratio, real numbers that exist on some type of continuum. Now, if it's any type of pretend continuum, people use t-tests for it because the t-test is quite robust. So if people give you like a scale that's like a Likert scale, right? And on the bottom side, it says strongly disagree, and then the middle is neutral, and the top is strongly agree. People say, well, it's scale enough. Like, yeah, it's 5 categories, but underneath it is a scale of agreement, right? And so people say, they'll let you get away with that for a t-test. Really staunch statisticians would be like, that is not technically correct, but it works. It does. They've done all kinds of simulation studies to show you still get the right decision. So if you can tell yourself there's a scale underneath this stuff, right? You can use it as an outcome. There's no scale that underlies eye color, right? That makes sense. Like you can't even imagine putting your eye colors on a scale that ranges from absence to, maximum amount of something, right? That makes sense? Okay. Do you have a question, Dawn?
What is the term you use? Things that exist. Do you know what you said?
On a continuum or on a scale?
No, on scale. In comparing when you use them and when you don't. Can you remember what you said? That's what you're.
For t-tests, your outcomes have to exist on some type of scale. They can't exist as categories.
That's it. Thank you.
Yeah, remember the difference between categorical, we reviewed on Tuesday, data types, making sure we still have that idea. That idea is critical moving forward because your data types, again, determine what statistics you can use, not the other way around. You don't go, oh, I want to run this test and then make your data be something. Your data is what it is. You have to figure out what type of analysis works to analyze your data. It's not a one-size-fits-all thing, okay? So, you got to understand that whatever we're talking about, and you should get this intuitively, because remember, we're dealing with a mean. What type of data do we calculate means for? Interval ratio, scale, continuous, right? That's what you calculate a mean for. So if you have to be able to calculate a mean for it, we all know average eye color makes no sense. We've been talking about that since the beginning of class. Which is part of why, again, I really think it's important to pay attention to stuff conceptually and not just try to memorize stuff. You need to put the story together and things get a lot easier to remember as opposed to just memorizing a bunch of random things. If you're learning and integrating the concepts, you can see that, oh, well, this is going to have to be a certain type of data because it uses an average. And I know that means are calculated. You guys all know that. You got it good on Tuesday, right? You all knew the mean is interval ratio data, right? Well, we're using means. I guess we need interval ratio data, right? Standard deviation, dispersion for interval ratio data, right? This doesn't have a median. It doesn't have a mode. It doesn't have IQR. It doesn't have stuff that would say it's another type of data, right? Okay, so that assumption is always going to be there. That thing you're predicting should be some type of scale, right? Some underlying scale. And again, we use that term. The reason I'm doing all these air quotes, people use it in a very fluid way. If you could imagine a scale underneath of it, they use it. Does that make sense? Okay. Questions? Okay. We're almost done with this then. So we're going to do some application stuff. You can run t-tests in a bunch of different ways. I'm going to introduce you to an online tool that's going to be a really fun friend. A lot of people like using GraphPad, and it might even be a lot easier than the Excel spreadsheet for some of you guys, and that's totally fine. Use what works for you. Okay, so I'm going to introduce you to this website called GraphPad that has some free data analytic tools that work really well. If for nothing else, you have to look up critical values for your t-test all the time now, right? Remember how you used to have to look up a z-score to figure out if it's significant and all that stuff? Well, now you've got to look up a t and a degree of freedom to figure out if it's significant. You can do that on the calculator I gave you. It has a spot for both. We'll go through that. You can do that on GraphPad, okay? But so GraphPad comes in handy for that. GraphPad also allows you to run a one-sample test, okay? And I'm going to show you that. You can do them in Excel. Now, Excel, the data analysis tab does not have a one-sample t-test. It only has independent and related. If you want to run a one-sample t-test in Excel, you have to use the one I built for you. On the t-test, it has instructions about how you can make it run a one-sample, and I wrote the math into it for you, okay? So if you wanted to do it there. SPSS, in my opinion, henceforth is the best, easiest, like hands down way to go. Okay? Like that's just, in my opinion, going to be true for every single thing moving forward. The math is going to get hard. This math is still easy. F-tests, the math gets a whole lot harder if you're going to try to do it from scratch. You do not want to do it by hand. You just don't. If you try, you're going to be sad. Okay? It's just going to take you so long to do your homework. I'm not saying it's impossible. It's not like you have to do, anything ridiculous. The math is all basic math, but it's a lot of steps. So it just takes you forever, and it's easy to make a mistake, and then your whole thing's wrong. So we're going to go to Analyze. We're going to be under Compare Means, and then the 3 t-tests are all there. One sample, independent sample, and SPSS calls it paired samples. Same idea, but we'll get there in a couple weeks. Okay, so let's look at these things real quick, and let's look at some different things that we can do. So here's a one-sample t-test on GraphPad. Okay, the nice thing about GraphPad is it gives you a few options about how you can calculate. Okay, so if you have a homework question that only gives you, because remember, you can only use SPSS if you have a data set, right? You can't use SPSS if they just give you a number. Like if SPSS said the sample mean is 8, the expected value is 10, and the standard error is 2. You guys with me? You can't use SPSS for that. You can only use SPSS if they give you a set of data, right? And you're supposed to analyze it. But you need all the numbers that you started with. Does that make sense? Okay. GraphPad, you can do it for any of that. So on GraphPad, I can click on enter the mean, SD, and sample size, and I could just put that in here, and I'm good. Okay, now notice a few things about this. So imagine I had a question like this. Actually, someone pull up your homework. Does anyone have their book with them to look up a book item, and we'll do a book item together? So pick one of the book items that just gives you numbers for computing a T and doesn't give you a data set. I think I gave you some. If not, I'll make one up.
Number 5.
Okay, how does number 5 read? I want one where they just give you an expected value, a sample mean, and a standard deviation. They don't give you data, they just give you values for those things. So it'll say like compute T. Can I borrow a book?
So number 2 is a sample of 25 scores.
Nine. So it would be at the end of chapter 9 would be the stuff where we want to do this. What number are you suggesting? 2. Perfect example. A sample of n equals 25 scores has a mean of 83 and a standard deviation of 15. Thank you. Perfect example. Good call. Okay. So part of the importance to using data analytic tools, I find so many students have very little idea of when they can use which tool. That's kind of a bummer. That's like me giving you a toolbox full of things and you don't know what any of them do. And you end up like trying to take your car engine apart with your fingers because you don't know how to use all the tools inside of that toolbox. You're going to have bloody hands, you're going to be pissed off, and the engine's not going to come apart, right? You need to learn what your tools do. You need to become totally acquainted with your tools, right? So we need to understand, what does a hammer do? You know, I don't use a hammer to try to fasten a nut in a bolt. It's not going to help me. You know what I'm saying? And that seems like no duh, but that's exactly the kind of thing we need to do with this. You need to understand, SPSS is only going to be helpful if they give you a data set. Step 1, critical thought, okay? Now, if you don't get that, you can use other tools. GraphPad is a great tool to use if you don't have a data set. So, read those numbers off for me again, Delaney.
Sample of 25.
Okay.
Mean of 83. And the standard deviation.
And what is our expected value to test against? Oh, this one's not actually having you get a T, so that's why you're actually confused. This just wants you to do the basics pieces of it. So let's find one that actually wants a T value. Okay, number 8, we're going to use as an example. I don't know if you have number 8, but number 8 works. I'm going to give this right back to you. So number 8 says, a random sample of 25 individuals is selected from a population with mean of 20. Treatment is administered. After treatment, the sample mean is 22.2, and the sum of squares is 384. Okay, so we're going to be able to compute a t-test here, but first we have to get sum of, so now look, our book gave us sum of squares. We can't use sum of squares to do this. We have to get standard deviation. Okay? So how can you turn a sum of squares into a standard deviation? Huh? Nope, you skipped something. That would be incorrect. This is why this stuff all builds. Okay, so we have SS equals 384. Was that correct? Remember that number right?
384.
Okay. So what can we turn SS into? Variance. Not SD, into variance. So how do we turn this number into variance? No. We divide by what? Divide by DF. Beautiful. So 384 divided by, what's our DF for sample variance? N minus 1. Okay, we got 25 people, right? So we're going to divide by 24, and that's going to get us variance right? $16. What do we do now, Jason? Thank you. So now to take the square off of variance, see, you want to get rid of the square, see how that makes sense to then square root? Yeah, there you go. So we square root it and we end up with 4. Standard deviation is 4. Does that make sense? That's our sample standard D. So now we can go over here. Our new mean for our, okay, this is your sample data. This is the hypothetical mean value. That's what you expect under the null hypothesis, right? Does that make sense? Okay, so that's your expected value. That's the parameter under the null hypothesis, which is this guy, the parameter under the null, right? Remember,